Piecewise functions. A piecewise defined function, also called a piecewise function, is a function defined by multiple subfunctions, where each subfunction applies to a different interval in the domain. Before we get into any examples where we create them, let's take a look at this. Of the 12 basic functions previously seen, the absolute value function is the only function that can be defined using two unique subfunctions. For the values in the domain along the interval negative infinity to 0, which is going to be this part here, the subfunction could be f of x is equal to negative x. That can be used. Okay, this would just be the linear graph that goes in a down direction with a slope of -1. And along the rest of the graph, from 0 to infinity, this part here, the subfunction that could be used would be f of x equals x. So that would be the linear graph with a slope of +1. Okay, so these two functions across different parts of the domain can be put together to create the absolute value function, a piecewise function, a function that's built out of pieces. And this would be the notation that we would use. If f of x is equal to the absolute value of x, which is this function here, then f of x could be restated in a piecewise format like so. F of x would be equal to negative x if x is less than or equal to 0. F of x would be equal to x if x is greater than 0. Okay, so you break apart the function into two different subfunctions. You also give the domain that you'd be using for them. All right, and one additional note here. The first says less than or equal to 0. So this point here is going to be part of this portion. It's going to be part of the function that's negative x. Okay, this part here can't have the equal to, because if it does that, in a weird way, we kind of fail to let this be a function. These overlapping parts, you want one of them to be closed and the other one to be open. Now, does it matter which is which? It does not. You could take that equal to away from this part, and you could apply it here, and you'd still get the graph of f of x equals the absolute value of x. Example 1, let's go ahead and try and sketch a piecewise function. The piecewise function we're going to look at, f of x, is going to be defined using two subfunctions. The first is going to be x squared, which is going to be for the domain, which is going to be for the interval x is less than or equal to 0. The second is going to be the square root of x, which is going to be defined for x greater than 0. So the transition between the two graphs is going to exist at x equals 0, which is going to be along the y-axis. Okay, so for x squared, for values of x that are less than or equal to 0, you're going to get that side of the parabola. Okay, you're going to get a point here. You do get a point there because it's included. Otherwise, what we would do is just make an open circle. Okay, so you get that point. You get this point. You're also going to get at -2 squared a 4. Okay, so you got that part of the graph, which continues on. It's going to continue on to the left and up because it's all the x's that are less than or equal to 0. So it continues to push in that direction. Okay, the rest of the graph, which is going to be x greater than 0, this direction here, we're going to use the square root of x. Okay, now the square root of 0 is going to be 0, so it does match up here. From this graph, you'd create an open circle here, but it's already closed because of the first part. In a sense, the square root of x is going to be the same graph that we get for the parabola, except on its side. All right, so let's take values that we can actually take square roots of. The square root of 1 is going to give you 1, so we go out to 1. The square root of 1 is going to be at 1. You can also go out to 4, and the square root of 4 is a 2. Okay, so the shape of the graph looks like this, except just positioned differently. Okay, as a follow-up question, is f continuous? Does it have any breaks along it? It does not have any breaks, which is going to make it continuous. Is it continuous? Yes. It does have an abrupt turn here, sort of like the absolute value function, but that doesn't change anything with regards to being continuous. It does exist at that spot. One additional note to that, if we didn't have the equal to part here, you would get an open circle in that spot, which would give it discontinuity, a removable discontinuity. All right, for example 2, we're going to sketch a picture of a piecewise function. When we're done with that, we're going to decide whether or not it is continuous. Okay, so our piecewise function, f of x, is going to be defined with three parts. You've got 2 if x is less than or equal to -2. You also have x squared minus 2 for the interval from -2 to 1, but not including those values. We also have x minus 2 for x greater than or equal to 1. All right, so one thing we should see in the piecewise function is that when one piece finishes, like this piece is just up until you get to -2, when that finishes, the next picks up. When this finishes at 1, the other one picks up as well. Okay, I'm going to start by graphing the middle part because it has open intervals here, just to describe what that is. Okay, so for that part, we've got the quadratic x squared minus 2. That is the basic parent function quadratic, but translated down 2 units. So you could imagine it located here with the vertex at 0, 0. It would have points at 1, 1, at -1, 1, then it expands out. But that graph is going to be translated down 2 units. Okay, so the vertex is going to move to here. Okay, and then the point that would be at 1, 1 is going to move here. The point that would be at -1, 1 would move here. Okay, now the interval that we're actually going to be using is -2 to 1. Okay, so the graph is actually going to end here. That part of the graph is going to end here. We do have an open interval at 1, so this is going to be an open circle there. Okay, now the graph is also going to go all the way to -2, which means I need to go further out a bit. That is going to be over 1 up 3, which will go to here. And again, that one's going to be open as well. Okay, so for the middle part, we have this parabola that looks like that. All right, so the part that's before it, where f of x is equal to 2, that's just going to be a straight horizontal line. It basically says that f of x is always 2. So straight horizontal line for any value where x is less than or equal to -2. Okay, so over here you're going to get a flat line, which is at a height of 2. Okay, and it's going to go all the way into that open circle. Because it has that equal to part, it's actually going to complete that spot. So that gets colored in. And here's your graph. Okay, now for the other side, we've got x minus 2. That would be a linear equation. It has a slope of 1 with a y-intercept at -2. Okay, so you can imagine it starts here at -2. It has a slope of 1, goes up 1 over 1, so it's going to hit that point, goes up 1 over 1, up 1 over 1. Okay, it's going to actually begin at x values of 1, which is here. So it's going to complete that circle, and it's going to continue to move that direction. Is it continuous? Yes, it is. Where we had the open intervals, the other parts of the function, the other pieces, actually completed those spots. Okay, so we do have some sharp turns. That would be a sharp turn there. This is a bit of a sharp turn as well. But the graph is still continuous. It doesn't actually have any breaks along the domain. Example 3, we're going to do a word problem. A service fee is based on the length of time. Up to 10 minutes costs $20. Over 10 minutes and up to 30 minutes costs $30. Okay, so for those first two parts, we have what we would call a flat fee. Up to 10 minutes, it's going to be $20. So whether it was 1 minute, 2 minutes, 3 minutes, or 10, it's going to cost $20. As soon as you go over 10 minutes, the cost is going to jump to $30, and it's going to stay there up until you get to 30 minutes. Once you get to 30 minutes, it's going to be a different price. It says over 30 minutes costs $30 plus $1 per minute over 30. What we're going to do is sketch a picture of this, which is going to be a piecewise function. We're going to call it f of t. When we're done with that, we're going to go ahead and write the function out, f of t. Okay, so for the first two parts, we have those flat fees. Up to 10 minutes, it's going to be $20. All right, so at 10 minutes, the cost is going to be $20, which is here. It's once you go over it, it's going to change. Okay, so everything to the left of that is going to be at $20. So that's your first piece. And in fact, we can start building our function right now. F of t, it's going to have three parts. The first is just going to be a flat rate at $20 for any t value that would be less than or equal to 10 minutes. Of course, you can't have a service fee that would be less than 0 minutes, so we'll go ahead and put that in there as well, which I guess would mean I should have an open circle in that spot. Okay, the next part is also going to be a flat fee, which is going to be $30. So it's going to be at a height of 30, and that is going to run up until you get to 30 minutes. Okay, so at 30 minutes, you got a cost of $30. Okay, now the transition at 10 minutes is going to jump up. You can have an open circle here. Okay, because it's only over 10 minutes that you're going to get charged $30. All right, so for our interval there, it's going to start at 10, open interval, and it's going to go up to 30 minutes. All right, so our third part is different. Once you get to here, it's going to change up. Okay, at that point, you're going to pay $30, plus you're going to pay $1 for every minute beyond the 30 minutes. For example, if you had a service of 40 minutes, there's an additional 10 minutes here, which you're going to get charged a total of $10 for $1 per minute. So on top of the 30, you're going to add another $10, which is going to get you to $40. So you'd have a point here. At 40 minutes, it's going to cost you $40. And this part of the graph is going to be linear because you have a starting value and then you're increasing by the same amount per minute. Okay, so the graph looks like that. All right, now, the intervals, that should be easy. That's going to be any t value that would be greater than 30. The equation that we would be using needs to be a line. So let's start with this idea, slope-intercept form. We'll start with the fact that we know the slope. The slope, m, is going to be 1. It's that $1 per minute. So we can change this to just x plus b. The slope would be 1. All right, so consider any point that would be on this graph. For example, 30, 30. When x is 30, the y is 30. So I can plug those in. And from here, I can figure out that the only logical b value would be for it to be 0, so that we can actually get 30 equal to 30. In other words, if b is 0, the equation is actually just y equals x, which for what we write here will just be x, or in this case, it's t.
Later, blah.